Hello, welcome to Introduction to Aerodynamics and Aerodynamic and Flight Mechanics. Today we're going to solve two example problems, essentially to make up for the lecture I had to cancel. I did record another video this morning and it is uploaded on YouTube and on Blackboard, but it doesn't have any sound, so I have to re-record the video and post it again. So the example problems we want to solve today are in page 26 and page 29 of the lecture notes. The first example problem is actually one of the book examples, and it is the example 4.6 of the book. The example tells us that asks us to consider a NACA 23012, which mean camber line is given to us. And then we are asked to find a couple of different things for this specific airport. Let's look at the mean camber line first. The equation for the mean camber line, z over c is equals to a constant. The constant is 2.6595, but I'm just going to use a for that value. Think of a as just a constant number, multiplied by x over c cubed minus another constant, again 0.6075. I'm just going to use b for it, x over c squared plus 0.1147 x over c. I'm going to use another constant for this, another letter for this, letter c, x over c. And this equation is true for a specific range where x over c is between 0 and 0.2025. There is another part to this equation that says z over c is equals to 0.02208. I'm going to use d for this to make things simpler. D 1 minus x over c. And this part of the equation is true for x over c's that are between 2025 and 1. So a couple of things. First of all, this is the equation for a mean camber. First part of it is polynomial, so there's a curvature. Second part of it is just linear. So two-part equation. This is the equation for the mean camber line, and this is a thin airfoil, so the airfoil is probably something like this, thin airfoil. Okay, we are asked to find angle of attack, first of all, at zero lift. What do we expect this value to be? This is an airfoil with a positive camber, so CL versus alpha is going to start from the negative angles of attack, and there will be a stall at some point, meaning that this alpha angle of attack at zero lift is smaller than 0. And if you go to page 24, I think, yes, 24 of the lecture notes, you can find the equation to find the zero lift angle of attack for a cambered airfoil. The equation is this. Alpha at L equals to 0 is equals to negative 1 over pi integral from 0 to pi dz dx cosine of theta minus 1 d theta. Sometimes in the equation you see a theta naught instead of theta. It's essentially the same thing as theta. There is no difference between the two. There is no difference that you should concern yourself with. So this is the equation for zero lift angle of attack. Okay. We have z over c. We have the equation z as a function of x, essentially. You have to take the derivative, and this whole integral is taken with respect to theta. So first step is to take the derivative of z with respect to x to find dz dx, and then we have to transfer everything to a system of z as a function of theta. And there's a transfer function, we're going to talk about that as well. But let's take the derivative first. So I'm going to come back here, and I'm going to delete this, and I'm going to write the derivative right here, so we can compare. dz dx, first thing you want to do is to multiply everything by a c. So we're going to get rid of this c, and then this is going to become c squared, x cubed, x squared, c, and x, and this c is also going to vanish. So we multiply all sides by a c. And then we want to take the derivative. The derivative is it's the derivative of a polynomial, so it's going to look like this. A multiplied by 3 x over c squared minus b 2b x over c plus c. And this is true for this range. And the next part of the equation, dz dx, is going to be equal to negative d. It's true for this range. So we have taken the derivative. We are ready to go to a system of z as a function of theta. Let's look at both values. 1 x over c. We know that x over c is always between 0 and 1, and we want to change this whole thing, this whole equation, to a theta that is always between 0 and pi. Okay, that's just by definition. If we use a regular cosine sine transfer function, let's say x over c is equals to cosine of theta. For x's of 0, theta would be pi over 2. Cosine of pi over 2 is equals to 0. So this won't convert to 0. 0 should become 0, not pi over 2, not anything else. And for this as well, if we put x over c equals to 1, then theta is going to become 0. So 1 does not become pi, which means that this is not a good transfer function. If we use sine of theta, the first part is going to become correct. So sine of 0 is going to be 0. It has correctly converted, we have correctly converted x over c to theta for 0, but it doesn't hold for 1, x over c of 1. X over the sine 1, if the transfer function is sine of theta, is going to be theta of pi over 2. It's going to give us x over c of 1. Okay? So what should you do? Let's write this transfer function. X over c, 1/2 1 minus cosine of theta. For x over c of 0, theta is going to be 0. And for x over c of 1, theta is going to be pi. Which means that we have found our correct transfer function. And you can always use this to take z as a function of x and convert it to z as a function of theta. So if we rewrite the curvature functions that we have, we're going to end up with a multiplied by 1/2 1 minus cosine of theta to the power 2 plus 2b 1/2 1 minus cosine of theta plus c. And then we also have to change this value to a system of theta, because we are not dealing with x over c anymore. We are dealing with theta. It's pretty simple. You just have to use a transfer function and set x over c to 0.2025. 1 minus cosine of theta is our transfer function. So we can find the theta, the new theta, to be 0.9335. So the first equation is true for thetas that are between 0 and 0.9335 radians. This is not degrees. Second part is dz over dx is negative d. There are no x over c's here, so the function is going to be exactly the same as a system of x functionality. Since we have two different functions, we have to take two different integrals. For alpha at left equals to 0, we're gonna have 1 over pi integral from 0 to 0.9335 dz dx, which is this function. I'm gonna call this dz dx1. Multiplied by cosine of theta minus 1 d theta plus this a second integral that goes from 9335 to pi or dz dx2 cosine of theta minus 1 d theta. Okay, so the rest of this integral is pretty simple. You just have to expand all of these terms and simplify them, add them together, multiply them together, and take the integral. The hard part of these integrations are where you end up seeing integral of cosine squared, integral of cosine cubed, and integral of cosine to the fourth. These three integrals are going to be a little tricky. So I'm going to give you the solution to the integral of cosine squared, cosine cubed, and cosine to the fourth. That will show up later on. You can just use these. I don't really expect you to solve the integral of cosine squared or cosine cubed or cosine to the fourth. So the solution to integral of cosine squared of theta is 1/2 sine of theta cosine of theta plus 1/2 theta. The solution to cosine cubed of theta is 1/3 sine of theta cosine squared of theta plus 2. And for the last one, cosine fourth of theta, the integral is going to be 1/4 cosine cubed of theta sine of theta plus 3/8 sine theta cosine theta plus theta. The integration part is not difficult, just a bit lengthy, and you have to know what you're doing. Whenever you get to these, you just have to replace them with a solution to the integral. You have to keep in mind that these are all determinate integrals, so there is no integration constants. Okay. If you do the calculations, you are going to end up with a zero lift angle of attack of negative 0.019 radians or negative 1.9 degrees. Doesn't really matter if you use degrees or radians, you just have to be consistent. The consistency is the key. Next part of the equation and next part of the problem is asking us to find lift coefficient at the angle of attack of 4 degrees. If you look at page 24 of the lecture notes, you're going to see that we have an equation for the lift coefficient, which is equal CL is equal to 2 pi multiplied by alpha minus 1 over pi or plus 1 over pi integral from 0 to pi dz dx cosine theta minus 1 d theta. If you look at this equation closely, you're going to see that this is negative of 0 lift angle of attack. So the equation for lift coefficient simplifies to 2 pi alpha minus alpha at 0 lift angle of attack. Okay. So we have this at 4 degrees. We have it as negative 1.09 degrees. And then we have 2 pi here. We have to convert all of these to radians, first of all, to be consistent with 2 pi. And eventually your CL is going to be equal to 0.559. This is part B of the problem. Part C of the problem is asking us to find the moment coefficient around the quarter chord. So Cm and C to the fourth. If you look at the page 24 of the lecture notes, you're going to see that we have an equation for this as well. And the moment coefficient around the quarter chord can be found using this equation, pi over 4 multiplied by a2 minus a1, where a1 and a2 are as Fourier constants, can be found using this integral dz dx cosine of n theta d theta, where n can be 1 or 2. We already have the dz dx. This part might be the tricky part, but you already know how to deal with these integrals. Essentially, just whenever you see a higher level, higher powered cosine, just have to come back here and take one of these to do the integration. So the integration part of it is a two-step integral because we have two different equations, two-step equation. And if you follow all of the steps, correct the steps, your Cm around the quarter chord is going to come out to be, I have to look up the value from my notes, to be negative 0.0127. You have to keep in mind that these are force coefficients or moment coefficients that are dimensionless. So there are no dimensions here. Last part of the equation is the problem is asking us to find the location of the center of pressure divided by the chord length. We have an equation for this again, which is x of Cp divided by C is equals to 1/4 1 plus pi over Cl a1 minus a2. Again, we have all of these. We have Cl, we have a1, and we should have had calculated a1 from this part of the problem, and a2. Plug and chug. Your x of location of the center of pressure divided by the chord length is going to come out to be 0.273. Compare this to the value we have for the location of center of pressure for a symmetrical airfoil. For a symmetrical airfoil, we proved that x over c, p over c is at the quarter chord. So it is equal to 0.25. You see, camber airfoil, this value moves a little bit. It is not at the quarter chord anymore. This is for the first example. Please let me know if you have any questions. And if you are doing the integration by yourself and you have difficulties by taking the integrals, please let me know. We can do one of the integrations in class step by step so it will help your understanding. The second example problem is related to the friction coefficient for the same airfoil. So we have the equation for the airfoil, for the camber of the airfoil. You have to keep in mind, using the analysis that we have talked about in class, we are going to assume that this is a flat plate. So we don't really care about the curvature here. The only thing we care about is the length of the camber line. And we're going to assume that this length is C. Okay. We are asked to find the drag, the friction drag per unit length for this problem, for at least the upper side of this airfoil. To be able to calculate the number for this, we have to have the velocity, density, and the viscosity. We don't have any of these, so we just have to run a parametric study. We just have to solve it using parameters of rho, mu, and v. Okay, whenever you see any problem like this, you want to check. The first thing you want to do is to check to see if there is any mention of tripping to turbulence. It can be an obstacle in the front. It can be a very rough surface. So obstacle at the leading edge, rough surfaces. These two scenarios can cause a turbulent flow from the beginning. And if that is the case, then you have to use the turbulent formulation, which calculates the CF using this formula, 0.074 divided by Reynolds number at C to the power 1/5. If you don't remember how to calculate the Reynolds number, this is the equation. Okay, and then you take this friction coefficient. You calculate the drag force using the definition of friction coefficient, just a rearrangement of it, by CF multiplied by dynamic pressure, 1/2 rho V squared, multiplied by C, this length again. Okay, so if there were an obstacle, if you had a very rough surface, then this would be the method. You can treat the whole thing as turbulent and solve it. But if you didn't have any of the obstacles, the turbulence generating things in place, then the first thing you want to do is to find the transition point, wherever the transition from laminar to turbulence happens. How do we do this? We usually agree that the critical Reynolds number for transition is 5 times 10 to the power 5. I might give you a different Reynolds number for your calculation in an exam or homework, but in general, we assume on a flat plate, the transition from laminar to turbulence happen at the Reynolds number of 5 times 10 to the power 5. So using this and using this equation, we can find the transition location, X transition. Then we have to check whether X transition is larger or smaller than the chord length, or this C, this length C. If it's larger than C, larger than or equal to C, then there won't be any transition on the plates, on the flat plates, on the surface of the airfoil. Okay, no transition. And if this is true, then we can just solve this whole flow as a laminar flow. We have to use the laminar equation for friction coefficient, which is CF is equal to 1.328 divided by the square root of Reynolds at the trailing edge. Then using this, we can find drag period span by multiplying this CF, laminar CF, let's call this laminar CF, by multiplying by the dynamic pressure multiplied by the length of the plates. The last scenario is the most complicated one, is where the transition happens on the plates. Which essentially means that we have two different regions on our plates. We start with the laminar bilayer, and then transition happens at X transition to turbulent bilayers. Our solution is going to have three different steps itself. The first step is calculating the laminar drag between 0 and X transition. So we have already calculated the location of X transition, so we already know this. And we know that between the X and 0X transition, we have laminar flow. So we're going to use the laminar formulation for the friction coefficient. But the Reynolds number is a transition Reynolds number, not the not the trailing edge layer, not C. So it is area of transition location, not area of the trailing edge. And then we calculate the laminar drag from 0 to X transition, multiplying CF by the dynamic pressure by the chord length. That's the first part of the problem. Second part of the problem assumes that all of the plates is turbulent. So it's going to assume a body layer. Let's say we have a body layer like this. Okay. For this part, we have to calculate the new CF using the turbulent formulation, using the Reynolds number at the trailing edge, and then calculate a turbulent, I'm going to call it the turbulent drag, CF 1/2 rho v squared C. But we do have a problem. We have two different numbers, I guess, from between 0 and X transition. And one of them is the incorrect calculation. The turbulent part is incorrect. So what we're going to do is we are going to assume a turbulent boundary layer from 0 to X transition. And this is essentially the fake turbulence part, laminar part, right? We are going to calculate the friction coefficient, the fake turbulence friction coefficient from 0 to X transition, and then remove this whole turbulent one, or remove the blue part, the laminar part, from the whole turbulent part from 0 to C. Okay, so part 3, use turbulent equation for laminar region. Okay, CF for this part can be calculated by the turbulent formulation. But the Reynolds number here is going to be the transition Reynolds number. Okay. And then using this, we can find a drag force. I'm going to call this fake turbulence, which is CF, the new calculated CF multiplied by 1/2 rho v squared multiplied by C. And eventually, the total drag force of the top of the airfoil is going to be equal to the laminar drag force, the turbulent drag force minus the fake turbulent drag force. So we have removed the laminar part from the turbulent calculations. And if this was a symmetric airfoil, we could have just multiplied this d top by 2 to get the total friction drag. But since this has a positive camber, we should not do, technically we can't do it, but it is still not a bad assumption as long as we are in the thin airfoil region. So for this problem, we can estimate the total drag on the airfoil by just multiplying it by 2, the friction drag by 2. These are the 2 example problems I wanted to go over with you guys on the during the Wednesday's lecture. I will also upload another video talking about the rest of chapter 4 so we can begin chapter 5 in class. Enjoy the rest of your day.